One. Hello and welcome to welcome to Calculus 2 section 10.4 on divergence test, integral test, and P-series test. So those three should be marked on your sheet, right? With so that's the first row and fourth row and the sixth row, right? So just make sure you mark that they're all 10.4. And we are going to now write those definitions and so on and go from there. So the first one is divergence test. Also known in some literatures as nth term test. So if you read Larson book or whatever, so it's going to be called the nth term test. That's the first test on your sheet. And this one simply says, if the limit as n goes to infinity of an is different than 0, then summation of an diverges. That's it. Put the infinity up there. This is the statement. So if the limit is not 0, if it's anything, it can be 1, it can be 10, it could be negative half, infinity. If it's anything other than 0, the series diverges. Example, summation of 3 to the n from 0 to infinity. Well, limit of 3 to the n as n goes to infinity is infinity, which is different than 0, which means summation 3 to the n diverges by divergence test. You also know that this problem diverges by geometric, right? We did geometric earlier. 3 is bigger than 1, so it diverges by geometric as well. But here is the nth term test or divergence test telling us the same thing. Summation of 1 plus 3 over n raised to the n from 0 to infinity. What's the limit over here? This is that special limit that everyone should know. Yeah? E cubed in this case because there is a 3 inside. That's not 0. And because it's not 0, we have diverges by divergence test. So all of these things, right? Now, give me. I want you to think about this for 1 second. Now, that one is the tricky business. So what do we have? We have, on this one, we have test is inconclusive. And this is insanely important. So we'll say limit n goes to infinity of 1 over n equals to 0. Now it equals to 0. test is inconclusive. Oh, I have more syllables. There we go. Test is inconclusive. We don't know. I'm going to prove to you that it also diverges. But this test can't detect it because the limit was 0. So it's very important to understand the way the test works. You look at the sequence, the limit of the sequence, and if the limit of the sequence is not 0, the series diverges automatically. That's all it is. So I'll give one more example. Summation of 3n plus 2 going from, 6 to infinity. You just go limit, n goes to infinity. 3n plus 2 is equal to infinity, not 0, diverges by divergence test. Done deal. Very important to know that when the limit ends up being 0, then the test is inconclusive. You cannot claim convergence with the divergence test, guys. It makes no sense. If you say it out loud, you see how ridiculous that is. Converges by divergence test. Really? No. Test is only for divergence. If you look at the sheet I gave you, convergence box is empty. There is no condition for convergence with this test. You cannot detect convergence with this test. I will write noob on your exam if you give me that something converges by divergence test. Yeah, okay, good. I'll write it in blood. This test cannot be used to show convergence.
So if the series converges, you need to show it.
You will be something else. You will use some other test. The last thing as a note, always try this test first. Remember how we had and will have that talk again for integrals? Always try u sub first before you go into trig sub, before you go into any other crazy method of integration we did. We always said, try the u sub first because that's the cheapest and the fastest method, right? Well, this is the cheapest and the fastest method for sequences and for series. And you should try this first on every, you get your exam and you have maybe 15 of these to solve on the test, right? You run this test against every problem first. It will knock off 2 or 3 problems off of the whole list. And then you go back and say, oh, this one is alternating, this one is telescoping, this one is geometric, right? And then you use their appropriate methods. But this nth term test, and that's why it's listed first on your list up there. Always use that one first. And you see that the 2 comparison tests are last. Those are the ones that are hardest to see and most annoying usually to do. Well, integral test is the most annoying one, but it's easier to see integral test. So the reason why I like this sheet of paper rather than what our book gives us is that it also gives you the order of recognizing tests. The most important test is ratio test, but that is, again, we'll see how and why. Just like for our integration, the most important thing and most useful thing for later mathematics is integration by parts. But I'm still listing u sub as the most important integration technique for us and the easiest one for us in Calc 2. But if you are to go to 300, 400, 600 level math, it's integration by parts that it's the boss, not u sub. So nth term test or the divergence test, you saw it's very easy. if the limit of the sequence inside the series, if the limit is not 0, the whole series diverges immediately. Make sure you know that it cannot show convergence ever. At best, it can be inconclusive, like in this example, and we are done with that test. The next one is the integral test. So what is happening with the integral test? Ready? We have a summation that starts anywhere. I'll just say some kind of A value there. No, A. I can't use A. Let's because this is going to be AN over here. So use I don't want it to be confusing. Let's use B. I don't want it to be confusing. All right. So, B is terrible too. I don't want to N. I don't. Let's go with M. M is definitely not going to be used anywhere here.
U with an umlaut.
No, M is going to be used for the.
Just use U with an umlaut.
Nah.
Multicultural.
Use them. All right. So you have some sequence. This M will represent different numbers. Could be 1, could be 0, could be 10. Right? So something will be there. We don't care where it starts. It's going to start somewhere. So that's why I put M there. Now, what's happening? First we'll say let AN be transferred into f of x. If f of x is decreasing, I'll spell it out. Decreasing, positive, and continuous, then summation of AN can be transferred into the integral from m to infinity of f of x dx. And they both either converge together or diverge together. You know how your AN is 3n plus 1. You will change that to 3x plus 1. That's what it means for the first line. So 3n plus 1 will become 3x plus 1. If you have 2 to the n, it will become 2 to the x. So you will literally replace your n's with x's. That's the first line. Then you have 3 proofs to do. If all those 3 proofs line up and pass, then you can replace the summation with the integral sign, and there's your improper integral, type 1, luckily. And then you run with the integration. If that integral converges, series converges. If that integral diverges, series diverges. That's what they mean, they converge together or they diverge together. Yes?
So if you run to an asymptote in between two of them, can you break it apart?
You have to.
Okay.
That's just the integral game, right? So if you have additional annoyance, well, right, such is life. You see type 1. Now, what we said 2 Saturdays ago when we learned the improper integrals, right, we said this changes your life forever from this point on, right? Anytime you see a definite integral, you can now expect a vertical asymptote. That includes this as well, right? because you are taking the integral from 0 to infinity of 1 over x minus 3. Well, you have an issue at 3 then, right? Which is between 0 and infinity, so that's a problem. And if that one makes it diverge there, then your series will diverge because the value is right there added to infinity. So one more time, this is like the path. You are changing your an into f of x by replacing n's with x's. Then you have 3 proofs to go through. Those 3 proofs, when you're done, then if they all pass, then you get to do the improper integral. And then if that improper integral converges, your original problem converges. If that integral diverges, your original problem diverges. It's very simple, right? Let's take a look at the summation of 1 over n starting at 1 going to infinity. This was the one that our divergence test couldn't solve because the limit was 0. Okay, so my an is equal to 1 over n, which means that my f of x will be 1 over x. Awesome. So what do I do now?
Bunch of numbers and create the series.
Well, I have a function. So now I need those 3 proofs, right? Number 1, you can do them in any order. It doesn't matter. It has to be all 3. Decreasing, positive, and continuous. Doesn't matter which way order you do them in. So is it, let's say, continuous? Well, what do you have? You can draw the graph if it's easy. So you see a discontinuous graph, but then luckily you learned Calc1 so well to know that you don't care about the whole graph if you have a restricted domain, right? You only care from 1 to infinity. You only care about this much of the graph. The rest goes to garbage. Now, is that much continuous? Yes, it is, right? The only asymptote 1 over x has is at 0. There are no other interruptions between 1 and infinity. So is it continuous? Yes. Number 2, positive. That means, is it always above x-axis? And the answer is clearly yes, because you can see that it's always above x-axis. It will never cross the horizontal, which is y equals 0. Number 3, is it decreasing? There are many ways in which you can deal with the decreasing. One of them is to take the derivative and show it's always negative. One of them is to go back to an and show that the next term is always smaller using the sequence theorem. In this case, we just see that it always drops down as the denominator increases, the value of the fraction decreases, so we are going to have the whole thing decrease. So yes. Yes?
Do we have to care about the actual proofs that we learned in Calc 1?
We will care about those for more complicated problems. In this case, there is no reason to do any of that stuff because we know 1 over x very well, right? But when you get ln of, n divided by n squared plus 1, right? In that case, yeah, the proofs are going to be needed. In this case, we don't care, it's just 1 over x. So, okay, so all 3 have passed. That means that our summation 1 over n from 1 to infinity can be replaced with the integral 1 to infinity of 1 over x dx. We learned at our improper integrals last class, or 2 weeks ago, that we do this limit b goes to infinity. You see why I couldn't use b before? Because it's going to be now 1 to b. That's why I couldn't use b. And we're going to have this as dx over x. What's the derivative of dx over x? Excellent. So copy the limit, b goes to infinity, and we have our ln of absolute x computed from 1 to b. And in 2 seconds, we're going to get our infinity. ln b minus ln 1. ln 1 is 0. So that's gone. And we have our infinity. Now, answer. Since all 3 conditions hold, and the integral 1 to infinity dx over x diverges, the series summation 1 over n from 1 to infinity diverges by integral test. This is your answer, guys. This paragraph here is your answer. Everything else prior to this is your what do you call it? Partial credit. Everything prior to that is a partial credit. So this box is 2 out of 8 points for your problem, right? And if the problem is 12 points, it's 3 out of your 8 points. Or your 12 points, sorry. It's either 2 out of 10 or 3 out of 12 for the box. So all 3 conditions hold, and then the integral was divergent, which means the series is divergent. It's a very structured thing. Now I'm just going to write this definition. Harmonic series. We mentioned this last class, but summation 1 over n to infinity is divergent. This is a very useful thing to have. This is like memorizing those side formulas that help you in life. Sure, you can crank the polynomial thing on the derivative of square root of x, but it's so much more convenient to just memorize derivative of root x is 1 over 2 root x. It's so much easier than cranking the negative 1/2 and, working out all of those things. So harmonic series, and next class after the test we will have alternating harmonic series, and those show up also in comparison problems. So you should do yourself a favor, right, with these. All right, another integral problem. Let's see. Well, let's do immediately summation of 1 over n squared. Let's start, let's say, at 2. It doesn't matter where you start. You just don't want it at 0 because it will be 1 over 0. Guys, these are exactly the same steps as the previous problem, right? And the graph for this one is also easy, so we don't have to do full proofs. You can just look at the graph. So we have an is 1 over n squared. That transfers into f of x equals 1 over x squared. And we are looking at the graph. There we go. Looks like Atari, right? And we are looking at 2 to infinity. This is technically the same rules as your 1 over x. So just write down those 3 and then try to do the integral, see what happens. Make sure your integral is now 2 to infinity, right? Because those are your limits, 2 to infinity.
Because we solve it.
So if you cancel it,
Sometimes you will have.
that's like here's what this is. No, this is divergence test where
Yeah.
equal to 0, then it's convergent. No, then I'm sorry. If it's equal to 0, it's divergent.
No, problem because everything has nothing to do with it.
I just want to know what happens if I this conversion.
So the integral, this is if the integral converges, then your series converges. If your integral diverges, then your series diverges. That's what it means. So we got the divergence.
Right.
So integral diverged, and because integral diverged, your series diverges. Okay? So if you find convergence, you get one.
Right, so, pretty much this is our original problem. So this is like, this part.
Let's go to the next level.
That's 1 over
The next level.
Turn this into
It's not even basic. You just
change x to x. 1 over x squared. And you need to do your conversions. So f of x leaves all 3 of these. Then we can turn our entire original experiment. So f of x is positive, all. So
it's completely irrelevant
Yeah.
as long as it's not divergent.
Yeah.
Because we are going to learn a crucial thing over here which deducts a lot of points on exams. But let's first write the answer. Since all three conditions hold and integral 2 to infinity of dx over x squared converges, the series summation 2 to infinity of 1 over n squared converges by integral test. Box, and we are done with the problem. Now, you said you made a silly mistake and you got to be 3/4 there. Okay, fine. 1/2 doesn't show up anywhere in my answer. And the reason is here in blood, and it will be underlined and boxed and everything. Series and integral do not converge to the same value. Seven exclamation points. There we go. Series and the integral. So do not write converges to 1/2 because it doesn't. And that's why your mistake would probably not be even noticed.
As long as all the math is right.
As long as you have convergence of the integral versus divergence of the integral, right? If you messed up on your algebra.
Basically, if you stumble on the right answer and then write the answer in the right form,
Yeah.
even if you did the wrong things getting to the right answer.
I mean, if I am to read your answer, then I would, mark it out -1, but most likely I won't, so. Guys, the only thing that is important here is that both of these converge or both of these diverge. Previous example, 1 over n, we had divergence on the integral. The series diverges as well. We're done. Over here we have a convergence. Integral converges to 1/2. That only guarantees that the series is going to converge. But we don't know what is the number it converges to. So we just say converges. And that 1/2 is nowhere in the answer because I'll bet my life that it's not 1/2. I mean.
Well, you start at a quarter.
And then you keep adding numbers. So. Series and integral do not converge to the same value. So now is the time to look at our paper again. We are going to go to the geometric and telescoping series, which are 10.3. And notice that those are the only two where you know what they converge to in the comments. Those are the only two that give you the sum. The other 8, when they converge, you have no clue what value they converge to. We don't have the formulas for it. You will have to use computer science, 3 million terms in a loop to figure out what the series actually does, okay? So mark that somehow on the sheet so you don't get burned, in any of these tests telling me it converges to a 7. Like, really? No. It doesn't converge to 7. It converges, but we don't know what it converges to. All right, so the next problem is going to be summation of 1 over n cubed. And now you're going to go, really? You went 1 over n, then 1 over 2, then 1 over n squared, then 1 over n to the cube now? How far are you going to go? Well, I'm just going to stop right here because I'm going to say an equals 1 over n cubed transfers into f of x equals 1 over x cubed on 1 to infinity. Then I'm going to put 3 dots here, like that. Say insert work here. And then I'm going to jump directly to answer and say, since all 3 conditions hold and integral 1 to infinity of dx over x cubed converges, the series summation 1 over n cubed from 1 to infinity converges by integral test. And probably you're still thinking this is completely unnecessary and excessive, but from these last 3 examples, I'm going to say P series, okay? So,
Go ahead.
I will. Here it goes. Are you ready? All right. So, P series. If your summation is 1 over n to the p, you have 2 options. P bigger than 1, convergence. P less equal than 1, divergence. And put this in a cloud, and this is your test number 5 for today. So we covered the first half of our tests. And if you are wondering why P series work like this as a definition, you have 3 examples above. They're all proved by integral test. Now we're going to do other integral examples. All right? This is just kind of sneaking it in the middle of the integration test just to show us for those 3 examples. So now if I am to ask you a question, this is a P series question, right? If I ask you 7 divided by n to the 9 from 3 to infinity, right? If this is your series, what do?
Divergence. It converges.
Okay, good. So you will just say P equals 9, which is bigger than 1, converges by P series. So this is another one of those, just like the geometric, right? You just look at it and you know. Now, I don't want to clutter this here because I'm going back to integral test now. Actually, no, I want to clutter this. I'll do it in purple. P series versus geometric series. P series 1 over n squared, geometric 1 over 2 to the n. Please see the difference. Right? They all have a 1, 2, and n in a different order, right? So please see the difference. This is 1 divided by polynomial. This one is 1 divided by exponential. I have to spell that out because I see all kinds of horrors going. Okay. Back to integral. Let's get us some spicier examples. I'm going to use the book over there to steal something nice. Divergence integral tests is very helpful that you already have. This is one of those sections that goes in like 15 pages. Okay.
Well, they have diabolical examples over here.
All right, so here's something that we don't have to go really crazy about. This is problem number 31 in the current example, the current edition of the book. We start at 3. We go to infinities. They have these k's all over the place, so let's use a k. We'll be switching it to x anyway. All right, so how do you recognize integral test? Well, you can integrate, right, easily. And this 1 over k minus 2 to the 4th power is something that you should be able to integrate using what? This is Calc 1 question. U-sub, basic U-sub, right? I know, right? All right, so AK is 1 over k minus 2 squared. What? And now we have that f of x is going to be 1 over x minus 2 to the 4th. Okay, so now drawing the graph and skipping all of those, right?
Bob, you said AK equals 1 over k minus 2
to the 4th power. It's clearly a 4. Here, I'll spell it out.
I'm just wondering if I missed a step. I just need to go 4 to the 4. I'm like, I just haphazardly guessed.
My brain is already my brain is already done with this problem. You have no idea. All right. The reason why every single one of my lectures is different and I have no notes and prescribed set of examples is because I teach this every semester. So I have to make this interesting for myself, right? To put different problems and not have the same problem done over and over and over again. So, all right, so what do we have here? Guys, we have to show continuity. We have to show decreasing and positive. Let's start with continuous. And we are going to go and dig back into what we learned in 2.6 in Calc 1, rules of continuity, right? So rules of continuity had the 2 theorems. One theorem said all polynomials are continuous on the entire domain. And another rule said, relevant to this, is that division is continuous if denominator is not 0, and function composition is continuous if the functions involved are continuous. So this is where we start. X minus 2 is continuous because it is a polynomial. So x minus 2 is continuous because it is a polynomial. Now, building it further, x minus 2 to the 4th is continuous because composition of continuous functions gives a continuous function. So we established right now that the denominator is continuous, right? Now we know that 1 over x minus 2 is discontinuous, right? But it's discontinuous where? And is that in our domain?
No.
Because we start at 3. How convenient, right? So 1 over x minus 2 to the 4th is discontinuous at x equals 2, but we have 3 to infinity as the domain. So 1 over x minus 2 to the 4th is continuous on 3 to infinity. This is a full proof, right? The entire proof that we need to do in order to show that the function is continuous, and we are using the rules from Calculus 1 from 2.6, 2 theorems, one that says that combinations and compositions of continuous functions continuous, and the one that says exponential, polynomial, logarithmic, sine, cosine, right, are continuous on the entire domain.
We have a polynomial and then a polynomial.
Yeah. Well, I mean, if you FOIL it into x to the 4th, blah, 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 it will still be a polynomial, so it's continuous. But you can also use the two sentences, one for the polynomial and then the function composition, right? And now we have for the division down there, and division is the one that you have to be careful because denominator can spawn a vertical asymptote. Is that vertical asymptote in there? Because if the vertical asymptote is in there, then continuity is broken. And if the continuity is broken, you don't get to do improper integral because you broke one of the 3 conditions. You don't get to use the theorem, right? You break one of the 3 conditions, bye, right? What are the conditions to drive?
Continuity decreasing.
To drive. I said to drive. Continuity decreasing, no. Conditions to drive is to have gas in your car, right? That's one of the conditions. To have air in your tires.
I thought
Right?
drive parentheses continuity.
No.
So like,
Oh,
yeah.
okay.
Like that's
But
what-
conditions to drive is to have gas in your car and to have air in your tires and stuff like that. Take any one of those conditions out, right? You can't go. So the same thing here. You break one of the 3 rules. You do not get to do integral test. Look for something else in that case. All right, so continuity done. Next one is we can do positive or let's do positive, right? Positive. Is it positive? Meaning, are all of the terms of this series always positive numbers? So what do we know? How do we know that? Well, denominator is always positive. Why?
Because we're starting after 2.
No.
It's raised to the fourth.
It's raised to the even power because it is raised to the even power. And then we have 1 divided by a positive number equals the positive number, so we're done. Yes. Whatever. So that's the positive part. And now decreasing. Okay, great. We are going to take the derivative. If the derivative on the domain is always a negative number, that means it's decreasing on the entire domain, and we're done. So we look at f prime of x. Now, the derivative for this, we're taking the derivative of x minus 2 to the negative 4, right? So we have negative 4, x minus 2 to the negative 5. And that's going to be negative 4 divided by x minus 2 to the 5. Do we all agree on that? So that's our derivative. And as you can see, the denominator is always a positive number. But you say, hold on, it's raised to the odd exponent. Yeah, but your domain starts at 3, right? And since domain starts at 3, 3 minus 2 is 1. The next number is 4 minus 2 is 2. So we say x minus 2 is always positive on 3 to infinity. So x minus 2 to the 5th is always positive, which implies that negative 4 divided by a positive number is always less than 0. F prime less than 0 implies decrease on 3 to infinity. Got it! Here, green check marks. Yes, yes, and yes. That's your integral test. Look at that. Beautiful. Finally, we can say, I even forgot what my problem was. Now we do integral from 3 to infinity of 1 over x minus 2 to the 4th power, dx on top. U equals x minus 2. Oh, I forgot to do the limit. B goes to infinity. Integral 3 to b of x minus 2 to the negative 4 dx changes into the limit b goes to infinity of 3 to b of u to the negative 4 du, which is the limit b goes to infinity of u to the negative 3 over negative 3 from, it's not 3 to b, but we'll switch it now. Limit b goes to infinity of negative 3 over u, not u cubed, x minus 2 cubed from 3 to b. We already see convergence, but I have limit b goes to infinity, negative 3 divided by b minus 2 cubed, minus and minus gives me plus 3 over 1, and the whole thing is 3, because negative 3 over infinity is 0, right? So this converges, and now we write the answer. Since all 3 conditions hold and integral 3 to infinity of dx over x minus 2 to the 4th converges, series summation 3 to infinity of 1 over n minus 2 to the 4th converges by integral test.
Shouldn't be 1/3, not 3?
Why 1/3?
Because it's in 1/3, negative 1/3, and then you goes back down on the bottom.
Oh, I put
I
the
did
3.
the same thing on mine.
Yeah, you're right. For sake of mathematics, it's important for 3 to be on the bottom,
But because the continuity is still.
but we don't care. Because, yeah, you're right. It is 1/3. But we can't tell anything about the actual number for the series, so it converges anyway. It just, we don't know where. let's take a look at another problem because we can. And then we're done with this section. The next thing would be for the next hour of the class, we'll just do the review. So let's take one more problem.
Oh, you see my costume on Thursday. I can quote the Calculus2s. Oh yeah, you saw.
I'm surprised they don't go for a father Gregory on it. Like half-life 2.
Yeah.
Imagine bringing like a shotgun on there.
Yeah, right. Bring
Yeah.
the Annabelle.
Yeah.
I won't get you far off campus or anything.
It's
Considering that I have more fucking trench coats in my closet than Van Helsing, like, I'm definitely like
on a watch list.
looking like some semi-charmed kind of pumped up kicks. There you go. That's the
Oh.
song.
Feeling it.
Why I don't like Mondays.
Can't move on to the talk. You don't have time.
It's cold out. Well, no, I have a literal World War I wool-lined trench coat that I found in a thrift store. It's great.
All right, this problem is going to appear as living hell, which is awesome. 34. Lock the doors. Summation of 1 over, I need a little longer line there. We'll again start at 3 to infinity. So we have k times ln of k, and then ln of k. You're just thinking of those 3 proofs, right, at this point in life?
Pretty much.
I was like, what is the worst thing I can possibly pick? Yes? No, we're not quitting. We're gonna do this.
You sure?
Mm-hmm.
I can be a bus driver and like 60 grand a year. I don't need this.
Exactly. As a plumber, you can make even more. But let's. I mean, guys, Thanksgiving is coming up. You're bound to be asked, like, what's new and how's life going. This can be your opening statement, like this problem. Pull up the chair. Here, I'll write it on this napkin. All right.
Is that ln k?
ln of k. Yes, it's a double nested there. Yeah. So you have k times ln k times ln of k. So it's 3 functions separated,
Can
right?
it be rewritten as ln squared k, or is that different?
That's different.
Okay.
ln squared k is ln times ln. This is ln inside ln. So. All right. Where do we start? Well, obviously we have our f of x. You already know. I have to compute. 1 over x times ln x times ln of x. Great. Now, the way to cheat is to graph this in Desmos, look at the graph, and say to 3 to infinity, yes, it's decreasing, right? But then we can also do all of this by hand, so let's go. Continuity. X and ln x are continuous on 3 to infinity. That's a theorem that you are calling from Calc 1. X is a polynomial, ln x is the logarithmic. On that list is also sine x, cosine x, and e to the x. They're all on that list. Square root of x is also on that list, like nth root of x is also on that list. So you can call that without proving each one of those. Now, we say compositions and combinations of continuous functions gives a continuous function. That takes care of the entire denominator, because composition is this nested ln x inside ln x. Ln x is continuous, and if you nest ln x inside itself, well, both ln x's there are continuous, so it produces continuous function. The word combination is addition, subtraction, multiplication, division, all of that stuff. And since x is continuous, ln x is continuous, and the composition over there is continuous, you have three continuous functions combined by multiplication. The entire denominator is continuous. And finally, we reach the denominator, right? 1 over x ln of x is discontinuous at x equals 1. But we are on 3 to infinity, so we're good, right? So f of x is continuous because the bad point 1 is not included. Bad point is also 0, right? But then, so you see the bad point is at 0, bad point is at and 1, yeah. And neither of those are included, so continuity is good. So we showed continuity using calculus. The next one is going to be decreasing. No, let's do positive, because that one is cheap. Positive. See, x is always positive on 3 to infinity. Is it? Yeah, right? The only numbers you can plug are 3 and more, and those are all positive, so we're good. ln x is always, oh, there's an y missing over here, always positive on 3 to infinity. You don't believe me? Here's your ln x graph, starting at 1. At 1, it starts being positive forever. Cool? Yeah. So how about multiplication and division of positive numbers is positive. Are we done? Of course we're done, right? We showed that this is always positive, this is always positive, this is always positive. Since all of these are always positive and you're dividing 1 by a positive number, all of the numbers involved in this multiplication division problem are positive. The final answer there is positive, and we're done. And now we get to decrease. Now we have choices.
Product rule for k ln x and then times ln x.
Well, the derivative over here might be a little bit tricky. Luckily, there are two worlds that we can use to show decreasing. There is a world of derivative for f of x. And there is also the world of just show that the next term is smaller if you use ak, right? The original problem. Because that works as well. Remember when we did decreasing sequence? We said an is strictly smaller than an plus 1. So, choice. Pick your poison. F of x, use derivative. AK, use AK must be smaller than AK plus 1. I don't care, right? Now, since we already used the derivative before, I want to use the AK, right? So my AK is equal to 1 over k ln k ln of k. My AK plus 1 is 1 over k plus 1 ln of k plus 1 ln of k plus 1. Need to show that 1 over k ln k ln of k is smaller than 1 over k plus 1 times ln k plus 1 times ln of k plus 1. So what am I going to do? Well, I'm going to cross multiply, right? When I cross multiply, no, wait, I need decreasing. I need decreasing. That means that the next term has to be smaller. I have this, the backwards, right? Because AK, which is term now, needs to be bigger than the next term to have decrease, right? Yeah, I have the sign wrong. So it has to be larger than. There we go. So now cross multiply. And we get k plus 1 ln of k plus 1 ln of k plus 1 is bigger than k ln of k ln of k. Do we see how each factor on the left is actually bigger than each factor on the right when you compare them one by one? So this is a true statement. And we're done with the decrease because this is a true statement. We needed to show that the next term is smaller, and the mathematics, once we worked it out, it shows the true statement, and we started from the premise that it's a true statement. We showed that it's a true statement, so that's it.
Wait, shouldn't it be smaller? Like the next k plus 1, one should be smaller, right?
This term here is bigger than that one. And this term here is bigger than that one. And this term here is bigger than that one. So since all of these are bigger, when you multiply them, their product will be bigger than the other side.
So it can't really decrease.
So is it increasing or decreasing the next term? It's increasing, right?
Decreasing.
Because it's a denominator that's getting larger.
Oh, okay.
Yeah, denominator is getting larger. Yes, we cross multiplied, so it's kind of hidden. We cross multiply, but yes, denominator getting larger means the numbers are getting smaller. Excellent. So all we need to do is to integrate 1 over x ln x ln x dx. And this problem is the exam next week, right? This is the improper integral. How do we integrate this? Dare I say it's obvious, but
You can try to use some.
thank you. Do we see 1 over x and ln x involved? Yeah. So basic u sub. You always try basic u sub if you can. You have your ln x and your du is 1 over x dx. And just plug everything in. So we have our limit. B goes to infinity. Integral 3 to b. 1 over x dx is the du. divided by ln x is u, and ln, and this inside ln is a u. What now?
U sub again.
U sub again, yes. G sub. G equals ln u. dg is equal to 1 over u du. Limit b goes to infinity. Integral, we know this is bad, but such is life. And we get dg over g. Right, your ln u is g, and du over u is dg. So dg over g. What's the integral of dg over g?
Absolute value of ln g.
ln absolute value of g. Computed from 3 to b, but we have to go back to x. So limit b goes to infinity. ln of, and what's g? ln u, good. Oh, and u is, huh?
It's just ln x.
It's ln x, yes. So triple ln. So ln of x. Computed from 3 to b. Limit b goes to infinity. ln of b minus ln of 3.
So it's going to go.
That's given number.
Yeah. Because ln on infinity is going to give you infinity, and then it's just going to another ln, right? Every time ln on infinity is infinity, so the whole thing explodes over there. And we have the answer. Since all three conditions hold and the integral 3 to infinity diverges, the series summation 3 to infinity of 1 over diverges by integral test. Which you already knew. Yeah, the integral, so I hope you see the breakpoint. If you studied those.
But that is conditional, isn't it?
What do you
So
mean?
basically, so as you explained it anyway, depends on, because it started at 3 to infinity.
No, it's not conditional on where it starts.
No.
It's conditional on what type of functions you have inside. We know for 1 over n, it diverged. 1 over n squared, it converged. So somewhere in between is the breakpoint.
Right.
So ln grows slower than x, but x times ln x is still not enough for convergence. It's just, once you do a million of these problems, right, for homework, it should get better. But that's it, guys. So this is what we had today. We covered half of our tests from the sheet, right, for chapter 10. We're going to now restart the stream for the review for exam, which is next week. Your quizzes will start tomorrow at 6 a.m. For the test prep. So remember, you need over 70 for them to count. So let's restart this.